All right. So representing chemical change, we're essentially going to be talking about balancing chemical reactions. Again, very much review. You would have balanced chemical reactions last year using a process called inspection. In other words, you just kind of look and you change the coefficients and make the numbers all work out. We're going to be doing the same. The only difference is I'm going to kind of give you my kind of interpretation. Oh, the animation on here is crazy. I'm going to bring the whole thing up. Why would water be the last thing to come up on that slide? I have no idea. The animations are all goofy. You can go ahead, you can write that down. This again is just a review, reactants products, word equations versus balanced chemical equations. As we go through our various PowerPoints, you'll notice various versions of our arrow here, right? That's just our reaction arrow. Sometimes when I type it in, it'll give me a nice little thin little arrow. These are actually arrows that we made using the line feature of a PowerPoint program. You know what I'm talking about. You've all made PowerPoints. Don't let that concern you. You don't have to draw a very thick arrow. It's just the way we built that PowerPoint. And also, hopefully, as you're writing, you're paying attention because what do you notice about my chemical equation here at the bottom? Yep, Janessa? It's not balanced. It's quite sad, isn't it? It says balanced chemical equations. It's not balanced. If you recall how to do this, by all means, balance it. Again, as I go through the notes, sometimes I supply you with the balanced chemical equation. Sometimes I don't. Keep an eye on that, all right? Somebody got it? Somebody got it there? Dallas, what do you got? 2 in front of the H2. 2 in front of the water. Excellent. All right? And again, this isn't earth-shattering, right? We've got to balance up the O's, right? There's 1 O in the water. We got 2 O's in the oxygen gas, so I need 2 of those. And once we've changed that coefficient on the H2O, we've got to balance it out with a 2 there. We'll look at this a little more closely in a moment. One more slide of some definitions and some various things. Again, very much review. Is everybody good to go? That's all right. Problem? Okay. So again, just a couple of reasons on why, whoops, sorry, gone too far, on why we balance. And the last two bullets here are essentially a brief description on how we balance it and what we can and cannot do. So again, why we must balance chemical reaction is the law of conservation of mass. Mass cannot be created nor destroyed, right? The reactant atoms can only kind of reorganize themselves into the reactant atoms of the products, the molecules of the products. You would have done a little experiment in maybe grade 9 or 10. I'm not sure. I think it's a grade 9 lab. It would have been like taking an Erlenmeyer flask, putting a little bit of a reactant in it, and then taking a test tube with another reactant, putting it in the flask, putting a stopper on it. Did you do such a thing? Yes, no? And then you weigh it, and then you mix it, and you weigh it again, and it's the same mass. Now, you might think that that's not a very exciting experiment. You might think that that is like the grandest of letdowns of experiments. But back when Le Chatelier was doing such a thing, when he was first getting a hold of a nice, accurate scale, right? Oh yeah, I said his name, you're right. Where is it? Back when Le Chatelier was doing his experiments, and he was using his nice fancy scale, this was kind of exciting stuff, that there was no mass lost. Because there was a great assumption that there was a lot of mass lost, right? When you burn something like a piece of wood, you end up with a lot less than you had at the beginning. So chemists, I guess they were chemists at the time, you know, budding new chemists, we're talking late 1600s, early 1700s, they thought that, you know, when a chemical change took place, something was disappearing, something was appearing. So that was big news. So again, Le Chatelier, we've been talking about him all the way along. We balance chemical equations, you know, if we go right back to the theoretical reasons, because of Le Chatelier. Okay, so now how we balance it. The big numbers in front are called the coefficients. When I teach the grade 10 applied class, sometimes I need to really make it clear. The big numbers in front, right, those big ones, they're called the coefficients. You guys know this. And you can change those in order to balance it. The subscripts, the little numbers that go with the formulas, that's what I tell them, the little numbers. You cannot change those. They're built into the identity of the compound. They come from the formulas that we just learned how to do. And that's why learning how to come up with our chemical formulas was so important. Because if we can't come up with a chemical formula, then we're going to be in trouble when it comes to balancing chemical equations. Okay. Tactics for balancing chemical equations. Now, I've read many various chemistry textbooks, and they all have this page that they have for ideas for balancing, and I'm never really quite pleased with them. And so these are the tactics that I use. This is what I do when I'm balancing a chemical equation, and I've never seen it in a textbook. You know, like in the last unit when I called them ugly Lewis diagrams, I made that up too. That's not as good as this. This stuff is better than that. If you have an element that's alone, balance it last. Whether it's monatomic, iron, FeCu, or if it's a Hofbrinkel gas, O2, F2, balance it last. I'll let you finish writing before I ask you why you think we should leave the ones that are alone last. So really, like I said, last year when you would have balanced chemical equations, you would have did it by something that we call inspection. It's really kind of a, how many are here? What do I need to put there? You just keep going back and forth until all the atoms are equal on both sides, right? And really, that's what we're doing here as well. We're doing it by inspection, but we're gonna keep some of the atoms together in terms of their polyatomic ions. We don't need to count them as individuals. We don't need to count up every oxygen because you can keep it together, say, as a phosphate. So if you've got phosphates here and phosphates there, there's no reason to separate them out. When dealing with 2 and 3, and we've already seen this, we've already seen it when we put together an aluminum with an oxygen. You've got that 2-3 situation. I need to have 6 electrons. We got to cross them over, right? Same thing comes up in a balanced chemical equation. Sometimes you have 2 of one thing and 3 of the same thing on the other side. How are we going to balance it? Use a common factor of 6. That comes up over and over again, and we'll see those. Last little rule here. If you're dealing with a Hofbrinkel gas and it's got, O2 or F2, and you've got an odd number, let's say you got 7 on one side, what do? Students usually panic over that. Don't panic. Just make it something 0.5, right? If it's 7, then it'll become a 3.5. You'll use 3.5 of them. Now, it's kind of against the rules to have a decimal number in your balanced chemical equation, so double everything up after you've got that 0.5. It's nothing to really get excited about in terms of what do I do next. In terms of this first one, why would I balance something that's alone last? Why would I leave it to the end? What do you think, Emily? You're exactly correct. They're the easiest to change, but why is it the easiest to change? Yep.
You can give it like any coefficient without changing the other one.
Exactly. You can give it whatever coefficient without messing anything else up. So leave it last. Okay, let's do some examples. Okay, we will start. Oh, we did that one. Let's just go straight to 2. Right on to 2. We did the H2O one just a moment ago. No fun. Again, e.g., you don't need to write down examples. It's just the way we type it in. Like I said, sometimes with our PowerPoints, way too much. Now I have a specific set of tasks also for combustion reactions, but I didn't want to write that down in the general tactics. But for combustion reactions, well, which one are you going to do last? This is one of our tactics. What should we balance up last here? Yeah, Janessa? Oxygen. It's by itself. So I always, just because when we have a combustion reaction and we've got that carbon-hydrogen type compound, I always do carbons first, hydrogen second, then go back and do the oxygens. So 1 carbon, so how many carbon dioxides do I need? Dallas? 1. Done. That's good. Our carbons are balanced. 4 hydrogens, how many waters do I need? 4 hydrogens, how many waters do I need? Dana, what do you think? 2. 2. Excellent. Whoop, pen not working. 2. Now we're balancing up the oxygens. Let me show you one other tactic that I like to use for combustion. Leave the oxygens as O2s. Imagine instead of counting O's, you're counting O2s. This is what I mean. How many O2s are found in this CO2? There's 1. So I've got 1 O2 that I need. How many O2s are found in these 2 waters? Dallas? 1. Because I got 2 O's, that makes 1 O2. So how many O2s do I need? 2. 2. And you'll notice I haven't worried about counting O's or counting C's, or I just worry about building carbon dioxides, building waters, and then see how many O2s that requires to take place. All right? You can always go back and check the good old-fashioned way. Okay, how many O2s on the left, how many O2s on the right? But if you follow this tactic, you'll be in good shape. Okay? We'll do another combustion a little later on in some of the other examples, or am I going to do one now? Oh, number 3. We'll do another combustion. That's fun. We'll follow it right up with another one. Again, for combustions, C's, H's, and then O's. That's a good tactic. Carbon dioxides. What do I need? Brody, what do you think? I need 2, because I got 2 carbons. Beautiful. Except my pen doesn't work. Not so beautiful. 2. Waters. How many do I need? Yep, Chris? 3. Okay, let's count up our O2s. How many O2s here? It'll always be the same as the number of carbon dioxide. Isn't that cool? How many O2s have I got here? 1.5. That's fine. So how many O2s do I need in total? I need 3.5. I need 2, and then I need 1.5. All right, so I need 3.5. 3.5. There's nothing wrong with that. It's balanced. Now, according to the rules of balancing chemical equations, we can't have fractional coefficients, so we need to fix it. But we don't have to worry about doubling this and doing all that other hard work to fix the problem. That fixes it. So what do I do now? I double every coefficient. So now I'm going to take this and I'm going to make that 2. What's that going to become? 7. And what's this going to become? 4 and 6. And that does it. And you know what? If you're doing this on a test and you want to write out the 0.5 and take your pen and cross them all out and double everything, I will just look at those numbers and say, yeah, good work. All right? Okay? Everybody okay with that? So combustion, which I don't know if it was a stressful way of balancing for you in the past, shouldn't be stressful. It's a very straightforward building of carbon dioxide and water molecules. Okay. Now on to some different ones, different types. So I look at that and I think again, what do I want to do last? What am I going to balance last here? Iron or hydrogen, which kind of forces me to what I have to balance first, right? If I'm going to leave those other 2 last, it drives me to look at this particular element. What am I going to balance first? Yep, Brody? Oxygen. Let's do that then. What do I need to do, Brody? If you just tell me what I got to put a number when you spot it. Yep, 4 in front of the water. I like it. Oh, we're now in peach color for now. Now we've got the luxury of balancing the other 2 last. Somebody just tell me what I need to do to finish it off. Yep, Chelsea? 3 on the iron? 4 on the H2. Again, the tactic of leaving what's alone last forces you into the O, and then it just falls to pieces. Questions, concerns, comments? No? Okay, let's roll on. Again, don't write examples each time. It's just bringing them up as we go along here. We'll do that one first. All right. This one looks chaotic. But if we look closely at it, hopefully we'll notice something. What are we noticing here? What tactic can I use here? Atlee? Yeah, exactly. I've got polyatomic ions all over the place, and they're staying together. You'll get some examples on our worksheet where the polyatomic ion turns into something else. Like we could start with an ammonium, And it could break apart into some nitrogen gas, into some hydrogen gas, right? Because it can have N's and H's in it. And this tactic then doesn't work there. You got to kind of go back to your which one is by itself. But notice all the polyatomic ions. ClO. A little bit of a reminder. What is ClO? If we're going to give it a name. ClO, Dallas. Hypochlorite. So I got a hypochlorite over there, and take a look. I've got a hypochlorite over there. I've got an NH4 here, and I've got an NH4 over here. Fe, Fe, and S, and S. All right. So we've got everything sticking together. Now we just have to dive in and kind of do something, because nothing's by itself. We just got to kind of dive in and see if there's any, maybe there's a 2-3 relationship. I really don't know. What would you like to do? Somebody have a tactic or a plan they'd like to start with? Yep. You put the 6 over here to start with? That's exciting. How did you know to put a 6 on the last one to start with? Tell us what's in your mind, Maggie. This is exciting. Oh, excellent. Good job. You did the 2 and 3 requirement. There's a 3 on the first one and a 2 on the second one, which means somehow we're going to have to end up with 6. That's excellent. I would actually probably deal with the 2 on the Fe, and then the 3 on the S, which then brings in your requirement, right? But you're exactly right. You've put this whole thing on its head. I wouldn't have put that one first. That would have been my last number. Dealing with the 2 here, what do I need in this one? 2. Dealing with the 3 there, what do I need here? 3. And that's where the requirement for the 6 comes from. Nice job. That's flipping it right on its head. Because notice, here I've got that 2-3 relationship. There it is. 6. Very good. Very good. In my mind, if I start looking at the 2, then the 3, I say the same thing. Oh, that's not going to balance out. Let's go look for something else. I wouldn't put a 6 quite yet, but that's what we have to do. Then I look at the Fe and at the S, and then the 6 comes out of it. Okay? Keep the polyatomic ions together. Don't start counting up necessarily all those H's and all that stuff. Unless you start getting into trouble, right? Let's say you're balancing away and it just isn't working, you're just not able to put it together, then go back to the basics. Count up all the N's, count up all the H's. But it can get a little overwhelming. Get that guy out of the way. Another combustion reaction. How do you know it's a combustion reaction? Yeah, Atlee? Yeah, very good. Carbon and hydrogen plus oxygen to get the carbon dioxide and water. Excellent. We'll be looking at that tomorrow when we go on and talk about different types of reactions. What's the trick in this one? There's a trick to this. Yep, Brody? You're going to leave the O to the end. That's correct. But what is going to warn you that, this doesn't look just like the last combustion reactions? Something looks a little different here. What is it that's a little different that's going to give us a little bit of a heads up? Yep. There's 2 separate H's. That's good. What else is there? There's something else here that we didn't have. Yep. There's an O in that molecule that we're burning. There's an O in here, which means we have to think about that when we get to this number. It's easier than you think. All right, let's go through it then the way we would plan on it. C's. 1. It's not that exciting. Oh, I don't put 1s in. It's good. Don't put 1s in. H's. So how many waters do I need? 2 waters, right? I've got 4 H's, right? 2 waters. Let's keep thinking in terms of O2s. I think that's a good way to do it. How many O2s am I going to have here on this side? How many O2s have I got? Yep, 2. You might want to put a 2 there, but that doesn't take into account this one. If I need two O2s, yet this thing is already providing me with an O, what do I need here in order to balance it up? Brendan? So 3 times 2 is 6, plus 1 is 7. Yeah, so no, 3 is not the correct answer. No. I need two O2s. Yep. 0.5. If I put 0.5, then I'm going to have one here, right? Correct? And one here, so that puts 2 oxygens on this side. And I've got 4 of them on that side. So 0.5 isn't going to work either. Yep. 1.5. If I have 1.5 O's, if I have 1.5, what does that get me here? 3 plus 1. How's it going, Jamie? And that's 4. So I still like to think in terms of O2s, right? Because what happens is you get 4, and then here you get 3 if you think of O's, and then you go, how do I make 4 and 3 work together? But if you think in terms of 0.5s, you can make 4 and 3 work together. Now what do I have to do to complete this? Double it all. Double it all. So I'm a fan of thinking in terms of 0.5 sometimes, and then just double it. So to complete that, we'll put the pen down here. We'll double everything. 2. What does this become? 3, 2, and 4. And you would have come up with that, except the math becomes then very ugly. Oh, what do I have to double? What don't I double? But if you leave the O2s together, you're in good shape. Okay. Let's do a couple of word equation problems. And then I'll give you a little worksheet, and I'll let you work for about 10 or 15 and leave you with some homework. And then I'm going to continue on with why reactions occur. Octane is a combustible liquid. It is the main component in gasoline. All right. You may have seen on the pumps it says the octane rating. That states how much pure octane is in that gasoline. And octane, and I'll tell you right now to start this, has a formula of C8H18. All right. So you go ahead, convert that word equation into chemicals, and balance it up. Again, it's a combustion. We hopefully are getting good at that. Again, once we start getting some skills here, get your pencils out if you don't want to make a mess of your notes. Go ahead of me. Don't wait for me always to write the information down. Okay, by the looks of it, when I look around where some of us are getting done, that's excellent. Someone tell me what to write here. Tell me, again, the coefficients. When you get to the arrow, we either say produces, all right, or to produce, or becomes, All right? So either way, either of those three would be fine. Could somebody give me coefficients and formulas for all of these things? In other words, I want you to read it right across. Brendan? Oops, hold on, my pen, I got pen malfunction. Still pen malfunction. Whoa. What's going on here? Oh, I know why, because I froze the screen. All right, I was cheating ahead. I wanted to see what I was going to do next. Okay, unfrozen. 2, go ahead. 2502 to produce, yep. CO2. 18H2O. I'm not going to quickly do a check on all those. You guys check for me. Do we like it? We like it? Excellent. Got a thumbs up. Good work. Okay. And I want to just do one more example. I'm actually going to jump ahead past example 2 so you can call this next example. Look, those are my 2s. That's where I was frozen. Those are where the 2s were ending up. We'll do this example here, and you guys know that I can't erase on this screen for some reason, so we'll just scribble it. We'll do that last example here. As you guys are writing that down, again, start putting down the formulas of the chemicals. You don't need to balance it, but we need a formula for calcium carbonate. We need a formula for phosphoric acid. As you're doing that, I'm handing out some practice sheets. First page, as you can see, is just straight put coefficients in front, right? Balance it up. The second page has word equations on it. Put them aside. All right, this is exciting. This is where two parts of your brain have to work together. And when two parts of your brain have to communicate, they very rarely communicate very well. So let me assist you. We all know how to come up with formulas, but for some reason, because we're now putting it in a chemical equation, it's becoming difficult. Calcium carbonate, formula for calcium carbonate. Janessa, what do you got? CaCO3, doesn't need brackets around it because it's 2 and 2, correct? Excellent. We've come up with a calcium carbonate. Now we've got to use that part of our brain that determines the formula for phosphoric acid. Yeah, William? H3PO4. Remember, it comes from phosphate, and phosphate is PO4. So I need an H3PO4. Excellent. Now a calcium phosphate. Calcium plus 2, phosphate minus 3, cross them over. Yeah, what do you got? Brackets 2. And now we're to the good ones. We're all happy to get to carbon dioxide and water. CO2, and I need a little bit of room down here, H2O. All right. You'll notice here that some polyatomic ions stay together, but some don't. Which one stays together? Which polyatomic ion is maintaining its structure? Atlee? Phosphate. And you know what? I'd use that as a starting point. So what do I have to do then to balance up my phosphates? What am I going to need here? Yep, Brendan? Yeah, 2 in front of the phosphoric acid. Good. What else am I going to do before I deal with this? Well, what falls apart? Which polyatomic ion is falling apart here? Yep. Carbonate. I want to deal with that at the end. I want to deal with that falling apart thing at the end. So what am I going to deal with next? Yep. Yeah, you bet. 3 on the calcium. Okay. Excellent. Now I got to deal with the carbon dioxides in the water. The carbon dioxides are coming out of this carbonate, aren't they? And that's what you need to do when you're dealing with something that falls apart. You need to ask yourself, what is this carbonate falling apart into? It's falling apart into a carbon dioxide, and then there needs to be a water that has to come out of these H's. Well, let's take a look. If I've got 3 carbonates, how many carbon dioxides must I get out of something like that? If there's 3 carbonates, how many carbon dioxides can that thing form? Yep, 3. Why? 3 carbons and 3 carbons. Sorry, that was kind of a mean question. 3 carbons, 3 carbons. I have to have 3. What fell off of the carbonate as it became carbon dioxide? Yep. 1 O. Where did that O have to end up? Yep. In the water. Has to end up in the water. How many carbon dioxides fell apart? Or so how many carbonates fell apart? 3. So how many oxygen atoms should be left to make water? 3. So how many waters should we be able to make? 3. There was another way to do that. If the H's ended up in the water, how many H's do I have? 6. And therefore, how many waters do I need? 3. Either way, it still works out the same way. When you have a polyatomic ion fall apart, and it does sometimes, you need to really think, what does it fall apart into? And then you can easily balance it up. Okay? All right? There are some textbook questions that go with this. There are the homework pages that I've just given you. I'm going to let you work, oh goodness, I'm going to let you work for 10. And you know what? If you're working really well, and I get a sense that it's better to have you guys keep working, I'll save the demonstration and the other part of the lesson for another day. Oh, just relax. You'll get to see things blow up. I'll make that judgment after 10 minutes of work. We'll see where you're at. Okay? Now let me tell you, those 2 sheets that I've given you, the answers to those are on the end of this PowerPoint. Here, take a look. See, answers. Oh, I hid them. So if you're looking for the solutions to those 2 sheets online, representing chemical change, note, right at the very bottom, all those answers are there. Okay? All right? You might look at those 2 pages and say, wow, that's a lot of work. This is the type of thing that practice makes perfect. The more you do, the better you get, and the faster you do it. And as you know from yesterday's test, the faster you can do things, the less stress you will feel at the end of the test. Right? Yeah. So practice is good. All right, I'm stopping the recording here.